Hussein Mazamol, enhancing resource management and energy consumption forecasting in multi-cloud environment with artificial intelligence driving approach. Very interesting. See now.
Okay, can you see my screen, please?
Yes.
Yes, everything's okay.
Okay, okay. Hello, everyone. This is Jaya Kumar. And today I'll be presenting our work on enhancing resource management and energy forecasting in multi-cloud environments using AI-driven approaches. The work is with collaboration with Junaid Hussain Muzammal, and we are presenting at DESSERT' 2024. So, introducing the topic to you, the cloud computing has redefined IT infrastructure by making it scalable and adaptable. Organizations today are integrated cloud resources more than ever, leading on the widespread use of multi-cloud environments. However, these environments bring significant challenges, especially in terms of resource allocation. The dynamic nature of demand and capacity in this setting requires advanced solutions to manage resources effectively. For instance, that demand fluctuates constantly and resources need to scale up or scale down based on real-time needs. This complexity makes managing resource a challenging task, as cloud providers need to maintain cost efficiently while meeting performance expectation and SLAs. So our study addressed this gap by focusing on key objectives, which is optimizing resource allocation and enhancing the energy efficiency. To achieve this, we utilize AI-driven approaches to predict the demand allocation. So moving towards the problem statement, in the cloud environments, resource allocation is a complex problem due to varying capacity and fluctuating demands across different clouds region. Without an optimized approach, cloud resources may, excuse me, ladies and gentlemen, for 1 second. Aag lag gayi hai? Sorry, I'm back. In cloud multi-environments, resource allocation is complex due to varying capacities and fluctuating demands across different cloud regions. Without an optimized approach, cloud resources may either be underutilized or over-allocated, resulting in higher cost and energy wastage. So energy consumption is now a major concern, and insufficient allocation leads to increased energy usage, which impacts operational cost, environment sustainability, and therefore accurate forecasting is necessary. Moving towards the research objectives, our research is to optimize, to improve, to enable, and to develop in terms of real-time adoption and to develop an AI solution. If we talk about the literature review, we have reviewed a lot of papers from last 3-4 years. I have to make it a summary, I have presented only top 8 papers that are relevant to us, and previous research has highlighted the significant challenges in terms of resource allocation. People have used ACOs, PCO, and there are many other solutions that have been used as well. This study, our study addresses the gaps identified these researches by combining the predictiveness and adaptive power of AI. So we integrate CNN, ACO, PPO, and GBM to bridge the limitation of existing methods to optimize the resource usage. So if we see the overview of methodology, we have combined the 4 algorithms. CNN, this predicts the resource demands across cloud region. ACO, which means ant colony optimization, it optimization the initial resource allocation and minimize the number of active region. And then there is PPO, which adjusts resource allocation dynamically in response to real time. And then finally the GBM, which forecasts energy consumption based on resource allocation patterns. I can show you the work summary. These are the two algorithms for PPO and for energy efficient management. So if we talk about data set, we have used the data set from Google 2019, which is cluster sample data set. This dataset contains workload traces from 8 Google clusters capturing CPU usage, resource request, job relationship over 5-minute intervals. This data provides comprehensive insights into the behavior of multi-cloud environments, allowing us to simulate a realistic scenario for resource allocation. By focusing on resource request and actual usage data, this dataset enables our models to learn from more realistic patterns. If we talk about the implementation details, we have used TensorFlow to build the CNN, PyGMO to handle the ACO optimization, RLib for PPO, scikit-learn for GBM, and data pre-processing are handled by NumPy. We have trained CNN on 100 epochs, and PPO and ACO configurations are set in the paper. You can contact me if you need more details. I have added a lot of details in the paper as well, but in case of any queries, you can contact me anytime. Talking about results and analysis, as the CNN is used for energy demand forecasting and over 100 epochs, the CNN model 83% accuracy with improvements in training and validation laws, which indicate the robust demands forecasting. If we talk about the optimization results in terms of ACO, you can see in 100 iterations, ACO significantly reduced the number of active cloud regions, optimizing resource allocation efficiency. Talking about the results of PPO, it has improved the allocation efficiency over time, which adapting dynamically to demand changing and maintaining the stable resource distribution. If we talk about the prediction accuracy, GBM show high accuracy with predicted values aligning closely with actual energy consumption, which outperforming the traditional benchmarks in the energy saving. If we compare the results with the previous model, we have achieved 12% higher energy reduction from Molta et al. Using, and they have used PPO and achieved 13.2%. In terms of energy efficiency, our ACO and PPO models outperform the optimization techniques from Shankdi et al. And Zhang et al., which lacked adaptability in multi-cloud environment. If we talk about energy forecasting accuracy, GBM predictors were closely aligned with actual usage, providing a better energy saving compared to the literature. In conclusion, our research addresses a critical gap in multi-cloud environments by indicating a CNN, ACO, PPO, and GBM for efficient resource management. Each model contributes to a scalable solution that optimizes resource utilization, minimize the cost, supports and sustainable energy predictions. This work fills an important gap in the field, offering an adaptable and efficient resource management system. Moving forward, we plan to explore more sophisticated real-time feedback loops to further enhance model accuracy and responsiveness. Thank you so much, and I look forward to any questions you might have.